Hello, this is Clint Halstead, and this is an internet-based course called Introduction to Microprocessors. We're using Designing Embedded Systems with PIC Microcontrollers, Principles and Applications, 2nd edition by Tim Wilmshurst. We're currently in Chapter 4. We did a lesson, the previous lesson was the first part of the book, Chapter 4, the hardware part of it. Now we're going to be working on the software portion of that. So software, there's two parts of that the book talks about. There's the writing the code, and then you've got the software tools. So writing the code, there's two languages commonly used, assembly language and C, and then of course there's others, but assembly and C are the most common. And then as far as software tools go, you need to have an assembler, you need to have a compiler. It's good to have a simulator. It's really nice to have an emulator or debugger. So you definitely have to have an assembler and compiler. Compiler is for C, assembler is for assembly language. But yes, you need to be able to take the assembly language code and transfer it down to machine language. So that's what we're going to start off with is doing assembly language. And we'll talk also a little bit about the simulator. So there's two aspects of the software, like I said before. The code, which is similar, and then C. Now we're going to use, for C, we're going to reserve that code for the PIC16 parts, because really the PIC16 parts have been optimized for C. For the PIC16 parts, we're going to be using assembler. So writing the actual code. Now, what is the issue or the problem is that we're trying to make a microprocessor chip do what we want. Okay, so this is kind of the pictorial diagram here. Is humans, they think in words, and they're not always very explicit or very exacting in what they say or how they say it. They just kind of have a general idea. We speak in English. So depending on what country you live in, you speak a different language. So ultimately, regardless of what language you speak, you're going to have to be able to learn how to speak in the microprocessor's language, which ultimately is binary. So really, the only thing that the actual microprocessor understands is zeros and ones. It doesn't understand anything other than that. So how do we get what we're thinking in our head, and we're thinking in English, into a binary 1 and 0 based format? So the way we do that is we use an assembler. We use a tool that takes some code, what they call them mnemonics, takes a mnemonic, or it's kind of like an acronym, and we get to write the code using Roman characters like A through Z, whereas the microprocessor, or the assembler, is going to translate that into the machine code for us. And you can also use a high-level language like C. And using a high-level language like C, when you use assembly, you still have to know the hardware of the internal workings of the microprocessor. Because really you're setting bits, you're moving bytes of data, so you're doing very rudimentary type tasks. Whereas in assembly language, or I'm sorry, C language, you're going to be doing things like if statements, if this then that, or while statements, or for loops. So you get a little bit more. You don't really care too much about the architecture. All you know is you want something to happen if this condition is true. So in C, you're really disconnected from the hardware, and really you're relying upon the compiler. So you have a compiler here to really try to figure out what you're trying to say with regular English words and translate that into a machine zeros and ones. So what options do we have for programming a microcontroller? So after we get the code written, we need to be able to program the data inside of the chip. So this talks about the assembler option. It says, this guy says, I'm writing in the assembly language, and then this is called a mnemonic. Move literal to W. Move W to F, port B. So, and then this computer is running a tool called a cross assembler, and it takes your statements, the instructions, these are the mnemonics, and translates them into the actual machine code, or the op codes and the operands. So the first part is op code, the last part may be the operand. And then you load it into the machine, you load it into your target device. So a lot of times this is called your target, whatever your final application is. This is your PC or your tools, and this over here is the programmer. Okay, so the programmer, PC and tools, and then the target. So that's the basic setup. Now what's the flow or the cycle developing a simple project? Well, the first thing you have to do is you have to write and modify your source code, which is assembly language .asm or .c. So you write this in a text editor, and then you assemble or compile it. If it's assembly language, you call it assemble. If it's C, you call it compile it. But this takes the what you're trying to do and converts it into the machine language, and then you can simulate it with a simulator to see if it does what you want it to do. And usually it doesn't, and you have to have at least one iteration, and then you have to change your code and then assemble it again. Sometimes the assembler tells you there's syntax errors. In that case, you go straight from here to there, and this is if you have errors. Many times you don't have syntax errors and you think your code's going to work, but the compiler doesn't tell you there's errors, but because there's not really syntax errors. You've written everything technically correct, but the function of it is wrong. It's not exactly what you really wanted it to do, and that happens a lot as well. So you may have errors that show up, and then you may have errors that only show up when you try to see actually what is your program trying to do, and then you realize, well, it's not really doing what I really wanted it to do. The code does exactly what you tell it to do, and that's a lot of times a problem. A lot of times we want to do something really different than what we write in the code, because sometimes it's really difficult to really get our thoughts and ideas into this really strict type of environment. Once we do have a good simulation, so we have a good simulation here and everything's great, then we're going to have to download that to our target hardware. And we can do that using our PIC kit. So we use our PIC kit 3 or PIC kit 2. And then we can test the hardware. Push the buttons, look at the LCD, see if it works. If it doesn't work, if you have a problem, then you got to go all the way back and start the whole process over again. So you may have many iterations, hundreds of iterations of these, and this is really the embedded development flow. To really understand, because we're going to start talking about some actual instructions, we're going to introduce 6 basic instructions from the first assembly language instructions that you will need to know. Before we do that, we need to look a little bit more about the internal operations of the arithmetic logic unit, the ALU, inside of the PIC16 series. So we're going to have this is the basic structure of how it works. You have an ALU which can do addition, subtraction, it can do ANDing or ORing. Okay? So one basic function would be to maybe add 2 numbers. So this kind of diagram kind of shows you where the data comes from, where can it go. So the W register can add to this string over here, which can either be from a literal or it can be from a register. So over here you have your special function registers, and you can add those 2 numbers and you can put the result either back into the special function registers or into the W register. And so that is, so there's two paths here on this side of the ALU. You can come from the literal or a special function register, and on this side it always comes from the W register. So really anything you want to add to something has to always be loaded into the W register. So that's one thing you're going to find to be always true. And then the result is either stored always in the W register. Many times it's stored in the W register, or it can also be stored in a special function register. Now it's interesting to note that the switch here can either switch is dependent upon this, what we call the D bit. So if D is a 1, then the result of the ALU operation is going to be stored in a special function register. If D is a 0, then the switch moves over to this position, and then the result is going to be stored in the W register. And we'll talk a little bit about how do you tell the microprocessor where you want to store the result. And it's going to be based on this, what we call the D bit. So one thing I forgot to talk about here is, so we're going to use the letter F with a bold to designate that we're going to designate a file register. So over here we're going to call this F. Okay, so this is memory location, this is RAM, and it's a 7-bit number. Now B, we're going to use a designation for a bit. Okay, because sometimes the ALU, its purpose is to simply set a bit. Maybe to set a bit inside of a special function register, or to set a bit on the W register. Now D, we already talked about D. D we're going to use to specify where the result is going to be stored, and then K is what we're going to use to specify a literal. Now what a literal is, a literal just means a number, so that means this path. So a literal just means like you have an embedded number, like 5 or 6 or 7 inside of your instruction. So when you write your instruction, you may say you want to add the value of 8 to the W register. So 8 in that case would be the literal, and that 8 comes from the instruction register. So up here you have the instruction register, and then that value of 8 is stored inside of there. 100 1000 is 8. So that 8 value would come directly from that instruction register. In this case, down through this path. So now we're going to talk about our first 6 instructions. Now these are all the PIC16 instructions. It's on. I have it on 2 pages. But so this is the first set, and these are the byte-oriented file register operations. Okay, so these all do operations on byte-oriented data. We're going to have a different section that's going to be bit-oriented. A byte is 8 bits, so all these apply to 8 bits of data, or what we call a byte. So what is our first instruction we're going to talk about? The first instruction is add WF. Now that's the mnemonic, okay? And so this is called what we call the mnemonic, and this is what we call the operand. So in this case we use the designation of F. And if you remember, F means file. And then D means, what does D mean? D means destination. So if it's a 0, it's a W register. If it's a 1, it's a file register. So this says, if you were to write this code out, you'd say add WF, and then you put a space, and then you put the file register address, and then you would put either a 0 or 1 here. You have to have a comma. And what that's going to do is it's going to add W to the value that's located in the address F, and then it's going to store that in either the W register or back into the file register. Okay, so it adds the contents of the W register to the contents of the memory location symbolized by F. There's a choice of where the result is going to be placed, and that is determined by the value of the operand D. Now operand, I don't know if we've really talked about operand. Operand just means operation data. So think of it as operation, and then they add a D on the end for just means data. So it's just a quick way of saying operation data. So this is the operation we're going to add, and the data is either a file register or the W register. And because of the different values that the result can take, all three condition codes Z, C, and DC are affected. So this chart also tells you what status register bits are affected. So all of these can be affected: the carry, the digit carry, and the 0 result. Let's also look at the. This is interesting to see here. This is actually the machine code. This is 14-bit. Okay, so this is what the instruction looks like in binary form or in machine code. It's actually a 0. So the AND W to F is a 0 0 0 1 1 1, and then the D gives the destination. So if you put a 0 here, then it's going to be stored in the W register. If you put a 1 here, it's going to store it back into the F register. So 0 and 1. And then F, you got F, 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 F. So what that does is it tells you this is going to be the address location for in RAM. Okay, so if you want, let's say you have a location 05 in RAM that has a value. So 05 is the address location. You would put 000 0101, because that's the binary for 5. So, and then if you want to store the result back in this location, if you want to put the result of that addition back in here, then you'd set this D to a 1, so you'd have a 1 here. But if you want to store it in the W register, so if you want the result to go over here in the W register, then you'd have to set this to 0. So this is the D, or the destination location. So that would be, then of course you have to have the 000111 on the front of it. So you have 0 0 0 1 1 1. So that would tell you that it's add WF. This would tell you the destination, and this would tell you the address location, which is the 5 here. So that's kind of internally, that's the way it works. Now let's look at our next one. Clear CLRF. Okay, so the operand is F. You have to give the location of the file register. So what this is going to do is it's going to clear a file register. So you just have to type CLRF, and then you have to give the address location of the file you want to clear. Remember, the file register, it's just a list of registers that have data in it. Let's say it starts at, let's just say we'll start at 16, 17, 18, 19. Let's just say these are all hex numbers. So if you want to clear some sort of a value in register 16, you just say CLRF, and you put 16, and it'll clear, which means it'll set all these to 0. So it'll just clear all that data. The word clear, let's just make sure we define this really quick. Anytime you use the word clear, it means 0. Set everything to 0. If you use the word set, that means make the value of 1. So that's the definition of clear. Clear means you make something 0. Set means you make something a 1. Because we're going to have certain functions that set things, and we're going to have certain functions that clear things. So yes, clear F, and then the address location of the file register. So these are called the file registers. We just call it FR. And it takes 1 cycle to execute, and this is what it looks like. The actual machine code is 000001, and then there's a 1 here, and then you have the file address location. And then it affects the 0 bit. So clear F, it clears the value of a memory location symbolized by as F. It is up to the programmer to specify the value for F, which needs to be a valid memory address. Again, because the result is 0, the status register Z bit is affected. So the next instruction we're going to look at is clear W. Now clear W does the same thing as clear F, except instead of clearing a file register, clear W just simply clears the W register. So we talked about before, we have this W register, which is kind of the scratch pad register, or it's the result register. Some people call it the accumulator, whatever you want to call it. It's where we talked about before. It shows you where the you have the ALU, so the result can either go into the W register or the F register, and the result comes from one side of the addition legs of the ALU. If you look at the ALU, how it's designed, always comes from the W register, and then it can go to the W register. So it's important that we have control over that one as well. So in this case, it's just going to allow us to clear the W register. Now clear again means it just sets everything to 0. Okay? You're actually going to have 8 of those, but I couldn't draw them all in, so 8 zeros there. Okay? 8 zeros. So the clear W clears the value to the in the W register to 0. There are no operands to specify. So operand just means there's no numbers or anything you have to specify here. It just simply, it already knows where the W register is located, so you don't have to specify it. Column 5 tells us that the status register Z bit is affected. Okay, so here you can see the Z bit is affected there. As a result of this instruction is always 0. The bit is always set to 1. So a Z bit of 1 means 0. No other status register bits are affected. You can see here that there's many other instructions that we'll talk about later, but for now we're just going to stick with those. I would take some time to digest this and look at this table, try to memorize as much as possible, try to look at how the operation codes, the machine codes are built up using these registers. Now remember, all these are 14-bit instructions. So that's the limitation, and this is how they're built. So it really helps a lot to kind of go through and kind of see how that they're built. Each one of these instructions has to have a unique code. So no one code can be used twice. So we just go through and kind of verify, okay, all of these are unique. There's none of them that are the same. So here's the remainder of the instruction set for the PIC16. We have some bit-oriented instructions. Whereas before we looked at the byte-oriented, now these are the bit-oriented. So what these ones operate on is only 1 bit. Okay, so before that we were operating on 8 bits, which is a byte. Now we're just going to operate on 1 single bit, either a 1 or a 0 location. So this command that we're going to study, called bit clear F. Notice there's also a command called bit set F, but bit clear F, it clears a single bit in a memory location symbolized by F. Okay. The bit number B will take a value from 0 to 7 to identify any one of 8 bits in a memory location. Okay, so what that means is if we want to clear bit clear F, if we want to bit clear memory address location 16, we need to tell it which bit. So if you look over here, you may have this, memory location 16, and it's going to have, 8 bits inside of here. And you have to tell it which one of these bits you want to clear, because this instruction doesn't clear the whole entire byte. It only clears one bit. So if you want to clear bit 1, the index here is, this is 0, this is 1, 2, 3, 4, 5, 6, 7. So that it goes from LSB, this is the LSB, this is the MSB. LSB means least significant bit, MSB means most significant bit. So if we want to clear bit 1, then we would have to put a 1 here. If we want to clear bit 4, this location is already cleared, but you could clear it again if you want. You put a 4 there. So whatever you put here is going to clear that bit. So that's the way that works. It says over here that there's no flags affected, even though you could potentially make all these bits 0, but the 0 register is not affected. So that's something interesting to note here, that the status register, no status register flags are affected. So don't forget the no there. No status register flags are affected, even though it is possible to imagine that the result of the instruction could be to set a memory location to 0. The next instruction we're going to look at is add literal to W, and then the operand is K, which is a literal. So you have to put the literal value. I mean, when we talk about literal, it's just a number. So if we want to add 8 to the W register, let's say we have the W register here, and we want to add 8 to that. So the ALU, this is the ALU, we would need to get the value of 8, and we want to grab the value in the W register and add literal to W, and then we're going to store the result back in the W register. Okay, that's the way it works. So this 8 value has to come from the actual instruction itself. So you can see inside of the instruction, so really the instruction is always in what's called the IR, or the instruction register. So this value of 8 actually comes from the instruction register, which is these bottom 4 bits. So these bottom 4 bits we're designating as K are in the instruction register. See, and then the rest of the instruction, 1, 1, 1, 1, 1, X just means it's not used. They don't really care what it is. So this is what would be an instruction register. Now, this is decoded. The upper part of this instruction is decoded and tells the ALU to go into addition mode, and then it tells it to grab the data from the instruction register, the literal value, and then it tells it to store the result back in the W register. So in this case, the D bit, the destination bit, is automatically set to 0. So you don't have to worry about setting the destination register to 0 in that case. So the add literal, WK adds a literal, i.e. an 8-bit number written into the program and represented by K to the value held in the W register. Like the add WF instruction, the Z, C, and DC status bit registers can all be affected by an instruction. So the carry, the digit carry, and the 0 status register bit can all be affected by that. The final instruction we're going to look at is go to K. So K is a literal. This instruction causes the program execution to jump to another point in the program whose address is given by the constant K. It is up to the programmer to give the value for K. No status bits are affected. So if you have some code here starting at 1, 2, 3, 4, 5. Now these numbers represent your flash memory. Your flash is where your program is stored. You have your zeros and ones in here. You have all these. You have all these these codes here. You have a bunch of these different opcodes or machine codes in here, and they start at 0, and program execution goes from, it just increments the program counter. So the program counter, the PC we call it, is going to point to 0, then it's going to point to 1. So you're basically going to step sequentially through this code until you get to something like a go to instruction or a call instruction, so, or a sort of a branch instruction. So in these bits skip, so you have these certain instructions will skip a line of code, and some of them will go to a different location. So this is one of the pieces of code, or this is one of the instructions that will cause you to not go sequentially. So you can get out of this sequential pattern of 0, 1, 2, 3, 4. You can actually go to whatever you want. So you may have a go to instruction here, go to. So you may be at 0, and then after you go to 0, you go to 1, because the program counter automatically increments by 1 each time. But if it says go, but you have a go to instruction that says go to 5, well, it's going to skip 2 and 3 and 4, and it's going to go, directly to 5. And then you can have some more of your code. So that's what it does. So you have to tell it the 5. So in this case, the 5 would be represented by all these K's. So you could put your 5, this would be equal to, you set that equal to 5. Of course, you'd have to represent it by binary. You wouldn't have to worry about that though, because the assembler would do that for you. You can just put 5, and then once the assembler runs the code, it's going to figure out that 5 is 0, 1, 0, 1. Okay? So that is the go to instruction. Now we'll talk about a little bit about some of the formats used for the instruction. So when you're writing actual assembly code, assuming that this is your text editor here, the leftmost margin, the first space when you start writing, the leftmost space is reserved for a label. So you can't start typing all your instructions at the first location. You have to tab over or something, because the first thing you type is going to be considered a label. A label is just, for example, down here, start is considered a label. Now, really, what your label is whatever line you're writing on has a line number, but it also, when it gets assembled, it's going to have an effective address location in memory. For example, you may have 0, 1, 2, 3. This is your program space. If you want to, let's say that your line of code, let's say you have a go-to statement here, or say you have a move statement here. If you want to know where this move statement is located in your flash and use that value to go back to this location later, you can put a label here called whatever you want to call it. You could put it X, what do you want to call it? In your code, it has to be the very first location. So in this case, we put start. So here in the very first location, if you type the word start, the value that's going to get stored as in start is going to be 1. So 1 will automatically get stored into start. So anytime you use the word start later in your code, it's going to be understood by the assembler as being a value of 1. So now you can say go to start, and then the way the assembler recognizes it, just recognizes it as go to 1. So it just looks at this start as being the value of 1. I know that may be a little bit confusing, but we'll do some examples later, and I think it'll really solidify exactly what is a label. So that's what a label is. A label is something that you type in the very first position in your text editor, your word editor. Notice that this second instruction here, add W to F, notice how it's been tabbed over. That's what you have to do when you start your instruction. You can't write add WF at this very first location. If you do, it'll consider that as being a label. Okay, but we want it to be considered as being an instruction. So that's the number one thing to think about as far as labels is a label has to start in the very first position in your text editor. But most of your code is going to be tabbed over or use a space bar to space over. Really, probably what I'd recommend is just, well, you can do either one. You could use space or tab. Probably tab would be a good way to do it. So the very first location is the label. Okay. And it's optional. And of course you have a comment is the very last thing. Or a comment can be on its own line if you want it to be. So notice down here, the comment here is select memory bank 1. So bit set F status register 5 bit. So this bit set F command is going to set the status register bit 5 to 1, which over here, this is just a comment. So if you want to do a comment, you just use a semicolon. That tells the assembler that just ignore this line, because this line is just for your information. It's just information for the programmer or for someone who reads this code. So it doesn't actually get implemented in your code. Okay. Okay, and this is a comment as well. You have a semicolon. It starts in the first location as well, so you can add comments in the first location as long as it has a semicolon. Now switch on red LED. And again, this is the label. Now this is instruction opcode bit set F. So instruction, and then the operands, and then this is the operand. Okay, so these are the instructions and these are the operands. So that's the format for writing in an assembler language. And it doesn't have to be case sensitive. So in this book we're going to typically use for just instructions we're just going to do lowercase, but it's not going to be case sensitive. Another thing that we're going to really need to understand is there's some things you want, some information you want to pass to the assembler that you don't want actually implemented in your hardware or in your code. For example, we talked about this assembler. The assembler is this tool that comes in between you, the programmer, MPASM is what they call it. This is the assembler. And then this is you, the programmer. And then, this is your final target device, your actual chip. But there's certain things. The purpose of the assembler is to take your instructions, move literal to W, for example. Take your instructions and translate them into a type of machine code. But there's other things we may want to tell the assembler, like what's the part number of the chip you're using, things like that. So those things, like where do you want to start your program code? If you have your code in your memory, where do you want to start the code execution at? Okay. When do you want to end the program? So those are called assembler directives. And so we want to distinguish assembler directives from lines of code, lines of assembly language code from instructions, I mean. So assembler language directives are not instructions. They are just information that is passed to the assembler. There's one way to pass information to the assembler would be to have drop-down boxes inside the tool, and you would drop down and say, turn the watchdog timer off, or do this or do that, include this file. But another way to do it is just simply to write out those commands in the actual code itself. So then you don't have to worry about setting all those options in whatever tool you're working with. So really it makes it more portable, it makes your code a little bit more portable. Portable means the ability to take your code and reuse it. So if you uploaded your code on the internet and someone else was going to use it, it's better to have all these different options included inside of your your text file than it is to have to set it manually inside of the tool itself. So that's what we call portability. The ability to port it to a new application or to give it to someone else and let them use it. So list just implements a listing option. We'll talk about that later. Pound include includes an additional source file. This is good for headers or things like that. Org we use to set the program origin. Really, a lot of times the org statement is going to be org 00, which just means start at 00. Sometimes we use this to skip the reset vector, or we may have a, I'm sorry, not reset vector, but interrupt vector. And then equate, this is a way to define an assembly constant. This allows us to assign a value to a label. So you can equate, status register to a certain value. Just put the number of the status register value here. And then the end statement just ends your code. So the compiler, the assembler knows that you're done with your code. So there is a way to set what we call a default radix or radix. So what is a radix? Is either decimal, hexadecimal, octal, binary, or ASCII. So a lot of times we talk about, we write numbers in decimal. 1 through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But you can also represent numbers as hexadecimal, binary. Okay, so this is going to be how you're going to communicate to the assembler what type of a number are you going to be representing. So, for example, if you want to do a decimal number, you use a D and then a tick mark, and then you do a 255, and then another tick mark. And that'll tell the assembler that you want the decimal equivalent of 255. And then, of course, there's two different ways to do hexadecimal. You can do H, tick 8D would give you 8D, tick, in tick, or you can use 0. This is a 0, by the way, not an O. 0x8D. So either way would represent a hexadecimal number. Now you can set any one of these as your default. So if you set this as default, then you don't even have to use the H. If you have this set as your default in your tool, then you could just type 8D. You wouldn't have to type any of this other information. But if you had it set for decimal, then you would have to type the H ticks and then the 0x. So it depends on how you set your default in your code. If you use anything other than default, then you have to use the letter and then the tick marks, either before and after. And then if you do ASCII, then ASCII is, like if you say hello or something like that. Okay, then you need to say use the tick marks, or you can use an A at the front of it as well, but you don't really have to. So that's how you represent numbers and ASCII in the assembler. Now, what is a typical flow for the tools? Well, typically you use a text editor. You can use the one inside of MPLAB, or you can use Notepad or Notepad++ or whatever you want to use. And you write your lines of code, and you call the file. You can call it file.asm. You need to make sure that it's a .asm file. It's written by you. And then you put it inside of your software tool, and you assemble it. And this assembler is just a software tool, and then it creates all these files. The hex executable file. The hex file is the actual machine code. So it's just a bunch of zeros and ones. You can't look at this if you open it up in a regular text editor. It's all going to look all jumbled, and it's not going to look like much of anything. It's going to look like a bunch of asterisks and symbols and stuff. But if you go download a hex file viewer, you'll actually be able to view the hex file. And you can download those hex file viewers if you want. The list file is going to give you something that's readable. it's going to basically give you this same basic thing, but with much more information. So the list file is interesting to look at to see how it actually gets implemented. So we're going to be looking at these list files. And then of course you have an error file will tell you what your errors are. So that's some of the most important files. There's other files that the MPLAB generates, but these are the most important ones that are used. So let's look at a really simple first program. A very simple first program. Notice that the first 1, 2, 3, 4, 5, 6, 7 lines here are just all comments. Okay, so all this is just a comment. It means it does not actually go into our program memory in our chip. So it does not go into the target device. This is just for your information. It says this very first program repeatedly adds a number to the working register. Put the initials and then the date. And then the date that it was tested. This is very good. You should always put your initials, your name, so someone knows when it was written, the revisions, if you have some revisions to it. Then notice the next line, they tab over. If they don't tab over, then this would be a comment, but we want it to actually be code, so we have to say org 00. So this is an assembler directive. It tells us to start in memory location 00. Okay, so it sets that to 00. So just imagine that these are your instructions here. So this is your flash inside of your chip. Okay, 0001, 02, 03. So the next line is going to be another comment. Program starts here, so this is just a comment. So nothing so far has actually went into the flash. So no data has actually come in here yet. Now it's going to say clear W. So now the clear W instruction is going to go here. Actually, you're going to get zeros and ones in here, but we'll just write clear W. And then the next thing here is it says loop. So this has to be a label. So this doesn't actually do anything. It just says, okay, loop is going to get assigned a value of 0, 1. So loop is going to be set equal to 0, 1. Okay. So here I'll just put the word loop outside of your flash memory. Now what's going to go in here is going to be an instruction called add literal to W 08. Okay, so what this does is it adds the literal value of 8 to the W registers. So the W register up here gets cleared, so this gets set to all zeros, and then the next instruction what it does is it takes a value of 8 and it adds it to W, which W is 0, so it's just going to add 8 to 0. 0 is going to be here, adds 8 to it. It's going to give you a value of 8, and it's going to store the result in the W register. So now this will go to 8. Now the next instruction says go to loop, so this is going to be go to loop. Okay. And then end doesn't actually get implemented. It just tells you that's an assembler directive as well. It says that's just the end of the program. So it just tells the program that's the end. So what's going to happen is the program counter, the org statement is going to set the program counter to 0. Program counter just automatically gets incremented by 1 each time. So the first thing that's going to happen, W register is going to get cleared. It's going to add that 0 plus the 8 to give 8, and it's going to store it in 8. And then it's going to say go to loop, which means go to, now loop is assigned a value of 1, so it's just going to go to 1, and then it's going to add literal to W again. So it's going to take 8, and now the value in W is 8, so it's going to take 8 plus 8 is going to give you 16. And it's going to store the value in the W register, so that's going to be 16. And then it's going to go down the go to loop, so it's going to go back to this 0, 1 location, and then it's going to take 16 and add it to 8 again. It's just going to continue that over and over again. So it's going to be a value of 24. It's going to be here. So that's going to get stored in here. And then this becomes 24. So it's just going to keep doing that over and over. So it's just going to keep incrementing that counter forever, for infinity, until you turn the power off. So that is the very first simple program. And next we're going to introduce the MPLAB tutorial, introduce the MPLAB software, but that's going to be in the next video. Thank you very much.